3, 2, unité, feu. Décollage.
Since its launch on December the 25th, 2021, aboard an Ariane 5 rocket, James Webb has exceeded all expectations. Despite initial doubts, this ambitious scientific project has become a game-changer in the field of space exploration. By harnessing the power of advanced technology, the premier observatory has opened up a new window into the depths of the universe. Its infrared eyes allow us to peer through the cosmic dust and gas that obscure visible light, providing researchers with unprecedented views of distant galaxies, nebula, and even exoplanets. The clarity and detail of Webb's images have stunned both scientists and the general public alike. From inexplicably bright galaxies to life on alien planets, and even the potential demise of our standard model of the universe, join us as we James Webb's most terrifying images ever seen in history that wept away many of our preconceptions about the early universe. We now live in a universe that is full of bright objects. On a clear night, one can see thousands of stars with the naked eye. These stars occupy merely a small, nearby part of the Milky Way galaxy. Telescopes reveal a much vaster realm that shines with the light from billions of galaxies. According to our current understanding of cosmology, however, the universe was featureless and dark for a long stretch of its early history. The first stars did not appear until perhaps 100 million years after the Big Bang, and nearly a billion years passed before galaxies proliferated across the cosmos. Astronomers have long wondered, how did this dramatic transition from darkness to light come about? After decades of study, researchers have recently made great strides toward answering this question. Using sophisticated computer simulation techniques, cosmologists have devised models that show how the density fluctuations left over from the Big Bang could have evolved into the first stars. In addition, observations of distant quasars have allowed scientists to probe back in time and catch a glimpse of the final days of the cosmic dark ages. The current models indicate that the first stars were most likely quite massive and luminous, and that their formation was an epochal event that fundamentally changed the universe and its subsequent evolution. These stars altered the dynamics of the cosmos by heating and ionizing the surrounding gases. The earliest stars also produced and dispersed the first heavy elements, paving the way for the eventual formation of solar systems like our own. And the collapse of some of the first stars may have seeded the growth of supermassive black holes that formed in the hearts of galaxies and became the spectacular power sources of quasars. In short, the earliest stars made possible the emergence of the universe that we see today. Everything from galaxies and quasars to planets and people. But if all cosmic history is a book, unfortunately, not all the chapters are visible to us. The cosmic dark ages make up the bulk of the book's missing pages. Imagine reading Shakespeare's Hamlet and skipping some initial scenes. You would transition from someone whispering in the darkness on the battlements of a castle in Denmark to a prince seeing ghosts and stabbing at tapestries. What happened? This is the situation that astronomers are facing. We now possess an excellent description of how it all started. The Big Bang Theory has successfully explained the features of our universe. Just a few numbers, called the cosmological parameters, can fully describe the universe's initial conditions, and decades of observations have confirmed with spectacular precision that cosmic history seems to have begun with a fiery expansion from a single, still mysterious primordial point. But a shadow fell across the universe as matter cooled from its early incandescence, and relatively simple initial conditions advanced into intricate complexity. This is the source of the rift in cosmic history, the darkness where astronomers wander. What's certain is that a few 100 million years after the Big Bang, a blink of an eye in cosmological terms, the Great Shadow began to lift. Enormous clouds of gas collapsed, and stars perhaps hundreds of times heavier than our sun sparked alight, beginning a photonic deluge that, over eons, illuminated the universe. In this brief cosmic period, all the protagonists of our story, including black holes and galaxies, started to peek through from behind the dark curtain of the cosmic stage. The first stars were mostly made of hydrogen and helium, the lightest elements of the periodic table, as heavier elements did not yet exist. As they shined, these stars and their subsequent kin transmuted those light elements into heavier carbon, nitrogen, oxygen, and other elements crucial to the universe as we know it today. These elements, these ashes from early stars, eventually formed everything we observe around us, you and me included. To fully appreciate this milestone in our chronicle of cosmic history, we must fill in the missing pages surrounding it. How did the first stars, black holes, and galaxies form? How big were they? How fast did they grow, and how was their evolution interconnected? How did the cosmic transition from simplicity to complexity lead to at least one world where curious creatures gaze up at the sky in wonder? Without such details from these few but fundamental chapters, our understanding of the universe and our place within it will be forever incomplete. This is the deepest, purest reason why astronomers are seeking sources farther and farther out. Fortunately, we are privileged to live in an era when telescopes of unprecedented power like the James Webb Space Telescope can aid us in this cosmic endeavor. Not long after coming online, James Webb immediately discovered 6 enormous universe-breaker galaxies, containing what seemed to be almost as many stars as the Milky Way, dating to just 500 million years after the Big Bang. The finding caused a stir in the astronomical world, with some scientists suggesting that it had put our current view of galaxy evolution or even our understanding of the universe into doubt. Besides throwing out seeds of potential new crises in astronomy, the telescope also cemented an old one: the Hubble tension. Put simply, the universe is expanding, but depending on where cosmologists look, it's doing so at different rates. In the past, the 2 best experiments to measure the expansion rate were the European Space Agency's Planck satellite, which gave a most likely expansion rate of 67 kilometers per second per megaparsec, and the Hubble Space Telescope, which studied pulsating stars called Cepheids, and found a higher value of 73 kilometers per second per megaparsec. Cosmologists thought this tension might be down to uncertainty, caused by Hubble not distinguishing between Cepheids and background stars, but the Webb telescope snuffed out that hope with a result of 74 kilometers per second per megaparsec. Since then, cosmology has lurched deeper into a crisis that could reveal new physics or even break the standard model. What might resolve it? More measurements by James Webb, of course. An equally puzzling discovery, in a first, the James Webb telescope may have glimpsed a rare type of star that astronomers aren't even sure exists. These stellar objects, called dark stars, might not have been fueled not by nuclear fusion, but by the self-annihilation of dark matter, the invisible stuff that is thought to make up about 85% of the matter in the universe. The candidate stars seen by James Webb will need more evidence to be confirmed, but if they're real, the finding could change our story of how the first stars formed. What's more, note that there weren't just inexplicably large ancient galaxies on James Webb's list of discoveries this year, but whopping black holes too. The first, Sears 1019, had a mass 10 million times that of our Sun and was found by the James Webb Telescope just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. We say "at the time" because James Webb didn't rest on its laurels. Earlier this month, the telescope discovered an even older massive black hole 440 million years after the universe began, How these gigantic space-time ruptures swelled to such staggering scales so early on is an ongoing mystery. Astrophysicists are currently exploring options that include the black holes being formed from the rapid collapse of giant gas clouds, although they haven't ruled out that some may have been seeded by hypothesized primordial black holes thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found more thousands of Milky Way lookalikes that shouldn't exist swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgangers were found by James Webb more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. But Webb's finding revealed that the disk galaxies are 10 times more common in the early universe than astronomers previously thought. The strange discovery joins others made by James Webb that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. As study co-author Christopher Consolis, a professor of extragalactic astronomy at the University of Manchester, said in the statement, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. These new James Webb Space Telescope results push the time these Milky Way-like galaxies form to almost the beginning of the universe. This implies that most stars exist and form within these galaxies, which is changing our complete understanding of how galaxy formation occurs. Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years." A quick note. Our own existence in a disk galaxy means that astronomers usually assume they must have good conditions for sparking life. If that's the case, it's possible that life could have started earlier in the universe than first thought. However, not stopped there, James Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, the Webb telescope found 42 pairs of Jupiter mass binary objects, or jumbios, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbios are too small to be stars, but as they bafflingly exist in pairs, they are unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets, or even for failed stars. Notably, while James Webb glimpsed deep space unlike ever before, it caused a stir in the whole scientific community as piercing through dust to find an ancient, ghostly galaxy. Look at this picture. It's a very blurry, highly dust-obscured resident of the cosmos whose name is only a string of numbers and letters. It even sits at a distance so far from Earth that it slips in and out of the watchful eyes of various telescopes. The image captured by the powerful James Webb Space Telescope spotlights galaxy Aztec 71, but what's striking here is that we're seeing Aztec 71 the way it was just 900 million years after the Big Bang. That's when the universe was turning on its very first stars, absolute eons before our solar system was born. The Webb's view of this galaxy as a hazy speck of light is a far cry from many other glorious images of galaxies and galaxy clusters in its repertoire. However, even this smudge holds important lessons for our understanding of the early universe. As study author Jed McKinney of the University of Texas at Austin said in a statement, "The fact that even something that extreme is barely visible in the most sensitive imaging from our newest telescope is so exciting to me. It's potentially telling us there's a whole population of galaxies that have been hiding from us." Elsewhere, James Webb has helped set yet another record. Pointing Webb's sights on a star cluster about 1,000 light-years from Earth, astronomers discovered some unusual objects, the smallest they've ever observed. The smallest of the new objects that we found is likely to be the least massive free-floating brown dwarf that has been observed to date. Say Kevin Luhman, an astronomy professor at Pennsylvania State University who is the lead author of a study documenting the team's findings. Brown dwarfs are one of the most unusual objects in the universe. Many objects we can see in the cosmos are some form of nebula, planet, star, or black hole. But brown dwarfs don't fall into any of these categories. The best way to describe them is star-like. They're not large enough to qualify as a star like our sun, and they're so large that astronomers won't categorize them as a planet. Another name scientists use for them is failed stars. This leaves brown dwarfs in an unusual in-between state that makes them especially interesting for scientists studying one of astronomy's most fundamental questions. One basic question you'll find in every astronomy textbook is, what are the smallest stars? That's what we're trying to answer. On the other hand, we all know that stars and galaxies aren't evenly spread throughout our universe. Instead, they're connected by an enormous cosmic web, a gigantic network of crisscrossing celestial superhighways paved with hydrogen gas and dark matter. Taking shape in the chaotic aftermath of the Big Bang, the web's tendrils formed as clumps from the roiling broth of the young universe, where multiple strands of the web intersected, galaxies eventually formed. Insights into the structure of this web not only give us a glimpse of the chaotic particle interactions that led to a universe existing in the first place, so astronomers using James Webb were stunned when they spotted the earliest strand of this web ever seen, a gassy tendril made of 10 closely packed galaxies spanning more than 3 million light-years in length. The filament formed when the universe was just 830 million years old and is partially wrapped around a bright black hole. By finding more, researchers hope to find answers as to how the very first galaxies formed. Another addition to the Webb telescope's long list of cosmic distance records this year was its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. How distant? A mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers to understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. Another feature of James Webb is its ability to measure a spectrum of the atmospheres of distant exoplanets, a toolkit which enabled it to spot the potential signs of life in alien farts on a Goldilocks water world 120 light-years away. The exoplanet it found, K2 18b, is a sub-Neptune planet weighing in somewhere between the mass of Earth and Neptune, orbiting the habitable zone of a red dwarf star. After taking an atmospheric spectrum, the Supreme Space Observatory found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich Hyson world that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a cabbage-smelling compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more peeks at K2 18b and worlds like it to find further evidence for extraterrestrial life beyond our planet. James Webb has mostly revealed insight into how everything began. But what about our eventual demise? Fear not, or maybe fear away, doommongers. The James Webb Telescope had you covered this year with a spectacular light show from a dying star, a preview into the demise of our solar system. The donut-shaped ring nebula, also known as Messier 57 or M57, is a 2,200 light-years distant corpse of an exploded star, harboring at its center a tiny pinprick of a white dwarf that is the last remaining piece of the star's core. As it reached the end of its life, the star exploded outwards, hurling its innards far and wide to form what looks like a gigantic eye. The explosion likely obliterated or ejected any unfortunate planets in its way, a fate that will similarly befall our own solar system in 5 billion years' time. While the James Webb's primary goal is to produce awesome science, and not just pretty pictures, sometimes the pretty pictures are the awesome science. Case in point, the stunning portrait of NGC 5068, a spiral galaxy sitting about 17 million light-years away. No ordinary galaxy. This one is spouting off new stars at a record pace. A team of astronomers was able to use multiple instruments on board the telescope to capture the galaxy in all its glory. The detailed images help astronomers understand the formation and evolution of stars, including solar systems like our own. It also makes for a fantastic cell phone wallpaper, and like all NASA images, it's publicly available, so help yourself. After all, as you see, NASA's James Webb Space Telescope pushed all our expectations in a variety of ways. Beyond the stunning infrared images, what really has scientists excited are Webb's crisp spectra, the detailed information that can be gleaned from light by the telescope's spectroscopic instruments. Webb's spectra have confirmed the distances of some of the farthest galaxies ever observed and have discovered the earliest, most distant, supermassive black holes. They have identified the compositions of planet atmospheres, or lack thereof, with more detail than ever before, and have narrowed down what kinds of atmospheres may exist on rocky exoplanets for the first time. They also have revealed the chemical makeup of stellar nurseries and protoplanetary disks, detecting water, organic carbon-containing molecules, and more. Already, Webb observations have resulted in hundreds of scientific papers answering long-standing questions and raising new ones to address with James Webb. The breadth of Webb science is also apparent in its observations of the region of space we are most familiar with, our own solar system. Faint rings of gas giants appear out of the darkness, dotted by moons, while in the background, Webb shows distant galaxies. By comparing detections of water and other molecules in our solar system with those found in the disks of other, much younger planetary systems, Webb is helping to build up clues about our own origins, how Earth became the ideal place for life as we know it. But it's worth noting that Webb's science mission is just getting started. There's so much more to come. We can predict what sort of incremental progress will be made and what present unknowns will be revealed by gaining this information that eludes us at present. But what we can't predict is what's out there that we presently don't have any clues about. We don't know what sorts of remarkable discoveries we'll be able to make simply because we're looking at the universe as we never have before. That's, arguably, the most important piece of doing science, the ability to open up what we call discovery potential. We know some of what's out there, and that's led us to some excellent expectations for what we anticipate that we're going to find. But what about the things that are out there that we presently have no hints of? Until we look, we don't know. Perhaps the search was best summed up by Edwin Hubble, but his sentiments apply precisely to the Webb telescope as well. With increasing distance, our knowledge fades and fades rapidly. Eventually, we reach the dim boundary, the utmost limits of our telescopes. There, we measure shadows, and we search among ghostly errors of measurement for landmarks that are scarcely more substantial. The search will continue. Not until the empirical resources are exhausted need we pass on to the dreamy realms of speculation. The life of the James Webb Space Telescope promises to be an intriguing one and lengthy. The observatory used very little fuel to maneuver itself into its exact target location, and that means there will be extra to allow the telescope to orient itself for far longer than anticipated. Space engineers have calculated James Webb's expected 10-year lifetime could be doubled. According to astronomer Professor Stephen Wilkins of the University of Sussex, In many ways, that is very good news. We will be able to do a lot more science with it now. However, the telescope will decay as the years go by as it is struck by meteorites and cosmic rays. That will slowly degrade its performance, so we should make the most of it while it is operating at near optimum conditions. Nevertheless, I think the most exciting science that will be done by the James Webb Space Telescope concerns exoplanets. We are going to learn so much about the chemistry of their atmospheres and are going to find some very strange and bizarre worlds out there. It is tremendously exciting. Cosmology has changed forever with the launch of James Webb on Christmas Day 2021. Ever since it opened its impressively sharp, high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathered sharp, pristine, and beautiful insights of early star and galaxy formation, and provided insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise: a bunch of the impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe. Our best cosmic predictions, based on lambda-cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake their understanding of galactic history. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and proto-galaxies, and these should be extremely blue and primitive, and again should only exist in low number densities the farther back we go. And finally, there should truly be a time where the very first stars and star clusters of all appear, and beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model, and to see if we truly understand the universe we inhabit, or if, and how, we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's SEERS, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Michaela Bagley of the University of Texas, one of the leading SEERS researchers, the theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early. One particular galaxy jumped out of the SEERS data straight away. Maisie's galaxy, named after the daughter of Stephen Finkelstein, one of the researchers, is 13 billion years old, making it one of the oldest galaxies ever observed. And it is much brighter and much bluer than anyone predicted. As Bagley said, when we found Maisie's galaxy, the surprising part was, how is it in the universe? It's exciting that this is the universe we live in. It's a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, which is equivalent to what human eyes can see. But as galaxies move further and further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. So Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Maisie's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us. But if we could see Maisie's galaxy today, it is much, much further away because in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift, and thus age, of Maisie's galaxy were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the SEERS team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's Near-Infrared Spectrograph, or NIR-SPEC for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data, dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Maisie's galaxy. It appeared to be 11.4. This means Maisie's galaxy is technically seen more recently in the universe than initially estimated, by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. The James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Maisie's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabio Pacucci of the Harvard-Smithsonian Center for Astrophysics said, we're seeing a rise of massive galaxies faster than we thought previously. The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter? Says Sandro Ticella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies. But there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into two types: spirals, which are disk-like with arms of dust and gas, and ellipticals, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs. But under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. In an attempt to explain the impossible massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They pushed the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidences at hand. So, up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, were shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. As Bagley explained, if the universe is smaller, the density inside galaxies and outside galaxies is probably higher. If it's dense and hot, the gas won't collapse to form stars. If it's dense and cold, then you could get a ton more stars. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe, because these elements were primarily formed within stars and spread by their explosive deaths, called supernovae. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. They were much bigger, heavier, and bluer than stars today, and they gave off more ionizing radiation. Those differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion, the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen, Bagley explained. There's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. But scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe, and telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today, and as the James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which Bagley refers to as baby pictures of the Milky Way. This is all about understanding how our Milky Way formed. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. In addition, on the hunt for alien civilization, NASA has just revealed that 17 discovered exoplanets could house subsurface oceans buried below thick sheets of ice. These worlds, much like the icy moons of Jupiter, could therefore be promising places to search for biosignatures, chemical signs of life. While the exact composition of these worlds remains unclear, estimates of their surface temperatures from previous studies point them being significantly colder than Earth. They're also each less dense than Earth, despite being roughly the same size as our planet. As Lynne Quick of NASA's Goddard Space Flight Center said in a statement, "Our analyses predict that these 17 worlds may have ice-covered surfaces but receive enough internal heating from the decay of radioactive elements and tidal forces from their host stars to maintain internal oceans." In other words, while their host stars may not provide conditions warm enough to keep water in liquid form on their surfaces, these planets may exhibit processes that can generate heat below their surface. The stretching and compression of rock inside a planet as it gravitationally interacts with its sun, for instance, could provide significant amounts of internal heat, enough to sustain a subsurface ocean. The radioactive decay of heavy elements inside the core of a planet can provide intrinsic heat as well. Thanks to the amount of internal heating they experience, all planets in our study could also exhibit cryovolcanic eruptions in the form of geyser-like plumes, Quick said. Cryovolcanism meaning, in short, ice volcanoes. The study drew on what we know from the geyser activity of 2 of Jupiter's moons, Europa and Enceladus. 2 of the exoplanets named in the research, Proxima Centauri b and LHS 1140b, were particularly promising candidates for having oceans relatively near the surface. Since our models predict that oceans could be found relatively close to the surfaces of Proxima Centauri b and LHS 1140b, and their rate of geyser activity could exceed Europa's by hundreds to thousands of times, telescopes are most likely to detect geological activity on these planets, said Quick. Follow-up observations of these worlds will likely include astronomers capturing the emission spectra of light traveling through these planets' atmospheres. Chemicals and molecules erupted into the atmosphere from cryovolcanic activity may hold clues as to whether life might exist in the cold, dark depths of these worlds. In a one-of-a-kind event, scientists just announced that Mars's atmosphere, once as thick as if not thicker than Earth's today, is leaking into space. About 0.11 kg of Mars' atmosphere is pushed away every second by the incessant solar wind, the speedy stream of charged particles routinely blasted from the sun, which pervade the solar system and even reach beyond Pluto. But for a rare 2 days last December, some of that wind went away. Its sudden and dramatic disappearance caused the atmosphere on Mars's sun-facing side to swell by nearly 4 times its usual size, from its usual 800 kilometers to over 3,000 kilometers. The peculiar event was recorded by a NASA orbiter named MAVEN, short for Mars Atmosphere and Volatile Evolution, which has been observing both Mars's atmosphere and its response to the Sun's behavior since 2014. MAVEN's data showed other aspects of the Martian system, including the teardrop-shaped magnetosphere, the bow shock, and the ionosphere, expanded similarly. As Jasper Halikas, a professor of physics and astronomy at the University of Iowa and a member of the MAVEN team, said, "We're really off the charts here. This is something that we haven't seen at Mars before with MAVEN." The atypical episode, the first in nearly a decade of MAVEN's career, occurred after a fast-moving region of a solar wind overtook its slower counterpart and swept up the latter's material, leaving behind a sparse region. The emptied storm reached Mars on D-Sector 25, 2022, giving scientists a thrilling front-row seat to watch the planet's atmosphere balloon out, the way it might have been if it were circling a less windy star. According to Halikas, who is leading a new study, this was a Christmas present for us. Nature set up this perfect science experiment. With MAVEN's data of the unexpected dynamics on Mars, Halikas and his colleagues studied how extreme solar events and their absence influence the planet's atmosphere, an insight valuable to understanding its evolution. The findings also have implications for our understanding of Earth-like planets outside our solar system and how they interact with their host stars, the team shared on Monday. We could look under the hood at what physics is going on, how the dynamics are working, and really get a sense of those details, said MAVEN team member Skylar Shaver of the Laboratory for Atmospheric and Space Physics in Boulder. 2 days after the almost vacant storm passed Mars, the atmosphere around the red planet settled down to its original state once again, but not before bouncing a little like a jiggling plate of jello. A similar storm struck Earth in 1999, when our planet's atmosphere grew to 5 times its normal size. But there aren't often orbiting spacecraft positioned as well as MAVEN is now to study such events, the new atlas reported. Shannon Curry, the principal investigator for the MAVEN mission, suspects events like this were common during Mars' early evolution 3 to 4 billion years ago, when our sun was more fiery than it is now and perhaps blasted out storms once a week or even every day. Such extreme events were likely responsible for parching the red planet, a world scientists presume once hosted liquid water and offered conditions friendly toward life. Extrapolating the latest MAVEN data to study Mars' evolution through time could shed light on how much its atmosphere eroded away and how fast the planet dried up, Curry said. Curry added events like this may occur multiple times in the next 2 years as the sun's activity climbs to its peak, expected to occur in July 2025, if not late next year. Last, as a piece of good news, the Hubble Space Telescope, following a string of setbacks concerning one of its directional instruments, has now resumed its job of capturing deep space images. NASA confirms that in a statement posted to the Hubble Space Telescope blog. The telescope's issues all began on November 19th, when one of the iconic observatory's 3 gyroscopes, a trio that live on from an original set of 6, began providing faulty readings. In general, gyroscopes are devices that use either circulating beams of light or rapidly spinning wheels to help scientists make sure an object is facing the direction they want it to face. Incorrect gyroscope readings on the Hubble telescope, as you might imagine, can therefore drastically affect science measurements. To image a specific spot in deep space with this Earth-orbiting telescope, you'd have to make sure it's actually facing that spot in deep space. Thus, Hubble entered safe mode on November 19th, something that's programmed to happen automatically when certain issues arise with the observatory. The team, however, was able to bring it back online the following day. But things weren't looking good shortly after, when gyro issues sent Hubble into yet another safe mode situation on November 21. The team brought Hubble back once more, shortly after that, only for the beloved telescope to retreat into its dark corner once again on November 23rd. That most recent safe mode entrance was slightly worrying as it persisted for longer than the previous two dips. It wasn't too worrying though because, first of all, this isn't the first time Hubble's gyros have raised issues leading to a shutdown. And secondly, maybe most importantly, the observatory can actually function with only one gyroscope. The team just uses 3 because it maximizes efficiency. Though it's been over 3 decades since Hubble began exploring the vibrant reaches of our universe, and though a new observatory in town has been catching most of the spotlight recently, this Reynolds Wrap-looking telescope is surely not finished yet. How did the universe grow up? This simple-seeming question was one that puzzled humanity endlessly for all of our civilization's history, right up until the middle of the 20th century. It was at that point that the cosmic microwave background was discovered, where it was quickly linked with being the remnant glow of long wavelength predicted by the Big Bang. Since that time, we've enhanced and refined our understanding, determining the age of our universe and what it's made of at present. This knowledge is enough to give us a set of expectations. How and when we think the universe should have formed stars, galaxies, and even groups and clusters of galaxies, paving the way for our modern cosmic web to take shape. But the key specifics of precisely how fast the universe grew up on stellar, galactic, and supergalactic scales remained beyond the reach of our greatest prior observatories like Hubble. But James Webb is changing that aspect of the story. For the first time, we're not just guessing, but actually seeing how the universe grew up. Thanks to the incredible capabilities of James Webb, we're constructing a more complete, comprehensive, and accurate picture of how our universe went from a small, star-free, almost perfectly uniform state to our tremendous, galaxy-rich cosmos of today.
We are going to discover incredible things that we never imagined.
But while James Webb is filling the gap in our understanding of the universe, it also detected several mysterious objects that could break cosmology.
That we can see with JWST, or we think we're seeing, are bigger than we had expected.
Is the discovery of unimaginably distant objects a mirage or a revolution? Stay tuned as we reveal the mysteries of these extraordinary discoveries and delve into the world-shattering revelations brought to light by James Webb. It's hard to believe, but it was only 100 years ago, back in 1923, that humanity first realized that the Milky Way galaxy didn't encompass the entire universe. That key discovery was made by Edwin Hubble, who, while observing what was then known as the Great Nebula in Andromeda, recognized that a periodic light flower he was seeing wasn't a nova, as he originally thought, but was rather a variable star located much farther away than any of the Milky Way's stars. It was the first slam-dunk evidence that these spiral and elliptical nebulae, observed for centuries, were actually galaxies all unto themselves, or as they were called at the time, island universes. Today, we know that the observable universe contains several trillion galaxies, with the earliest dating back to when the universe was less than 3% of its present age. With our own naked eyes, we can only see the stars and nebulae of the Milky Way and a few other nearby galaxies, all within our gravitationally bound local group. But thanks to a variety of observatories, including the Sloan Digital Sky Survey, Hubble, and now James Webb, we can see what the universe is like both near and far. And while we've only mapped out a tiny fraction of all the galaxies that exist, we've seen enough that we can not only describe what the universe is like at each moment in cosmic history, but we can compose three-dimensional visual reconstructions that show how the universe's galaxies appear and grew up over time. As you can clearly see from these videos, galaxies come in a great variety of shapes, sizes, and groupings, with large numbers of giant elliptical galaxies found within rich galaxy clusters, and the more familiar spiral shapes found more commonly on the outskirts of galaxy clusters, and in what astronomers call the field, or the regions of space that aren't associated with any rich clusters. This shows off what the universe looks like today, but if we want to know what the universe looked like in the past and describe how it grew up, we need to look even deeper. One of the most remarkable parts of the cosmic story is that the universe, as it is today, is not the way it's always been. Our universe started out in a very different state than what we experience today. Instead of being sparse, filamentary, cold, and with rich evolved galaxies that are grouped and clustered together, the early universe was different in every way. Today, we observe that the universe is expanding, and we know that the rate of cosmic expansion is directly related to the overall energy density of space itself. Well, back at earlier times, the universe was denser, expanding faster, less clumpy and clustered, and also hotter, as the photons within it hadn't been stretched to the long wavelengths they now possess at present. One of the most remarkable types of studies we've been able to perform are comparative galaxy studies, looking at the galaxies found within the universe today and comparing them to galaxies found farther away and whose light was emitted at significantly earlier epochs in the universe. Unsurprisingly, we find that galaxies have evolved from a population-wide perspective significantly over the billions of years that have passed. One of the best ways to see this for ourselves is to perform what's known as a pencil beam study of the distant universe. In this technique, we observe one single tiny region of sky that happens to be devoid of any relatively nearby stars or galaxies. We observe it for long durations of times in a variety of wavelengths, including, and perhaps especially, in long infrared wavelengths of light. Wavelengths that are excellent for discovering and imaging galaxies, whose starlight has been stretched to longer wavelengths by the cumulative expansion of the universe that occurred since their light was first emitted. Throughout the 1990s, 2000s, and 2010s, the best views of the distant universe in this fashion came courtesy of the Hubble Space Telescope. The deepest view ever taken, prior to the launch of James Webb, was of the Hubble Extreme Deep Field, which observed a region of space so tiny that it would take 32 million comparably sized regions to cover the entire sky. In that little narrow pencil beam of space, more than 5,000 galaxies were revealed. They span all of cosmic history, from the relatively nearby universe to more than 13 billion years ago, much closer to the Big Bang itself than to the present day. By measuring the distances to these galaxies, we've been able to recreate what a three-dimensional fly-through of those galaxies, near and far alike, would look like. But there are several limitations from taking this approach. First off, we aren't seeing all of the galaxies out there. Even in this deep view, we're probably only seeing somewhere around 1% of all of the galaxies that are out there. Most of them are small and faint, whereas the easiest ones to see are big and bright. We know we are significantly biased in what we're able to detect. Second off, most of the galaxies that exist are probably satellite galaxies that orbit around the large bright ones, and we don't have the sensitivity to observe them. We struggle to even count the number of galaxies in our own local group, so the small, low-brightness galaxies that represent the most common type of galaxy are largely invisible. Third, for the first 550 million years after the Big Bang, less in some places, more in others, the universe was filled with light-blocking neutral matter, similar to what's found in the disk of the Milky Way. We can only see the light from these early epochs that's bright enough to pierce through that light-blocking veil. And fourth, the brightest galaxies of all are the ones that are actively forming stars over the entirety of the galaxy itself, a starburst galaxy. The earlier we look, the more likely we are to be seeing a starburst galaxy, and the more likely it is that the starbursting has been triggered by a major merger of two comparably sized galaxies. Although all prior observatories have succumbed to these limitations, including even Hubble, this is precisely the class of observations that NASA's James Webb Space Telescope has been designed to overcome. Looking at the universe with larger eyes optimized for infrared wavelengths and for penetrating this light-blocking neutral matter, James Webb has discovered many galaxies that have surpassed even the limits of Hubble. Observing programs like JD's, Sierra's, GLASS, Panoramic, Cosmos Webb, and more are showing us how the universe grew up like never before. And unsurprisingly, it's not only taught us some incredible science so far, shattering several cosmic records in the process, but it's enabling us to visualize the young universe as never before. As Steve Finkelstein, principal investigator of the SARES collaboration, has put it, the sheer number of galaxies that we're finding in the early universe is at the upper end of all predictions. We're used to thinking of galaxies as smoothly growing, but maybe these stars are forming like firecrackers. Are these galaxies forming more stars than expected? Are the stars they're making more massive than we expect? These data have given us the information to ask these questions. Now we need more data to get those answers. Indeed, when James Webb finally started taking data, a number of extremely suggestive candidate galaxies for most distant of all emerged, but it would take spectroscopic confirmation to be certain of properties like distance. Looking in the James Webb Space Telescope, Advanced Deep Extragalactic Survey, or JADES field, a series of galaxies were imaged spectroscopically, with a new record holder emerging at a confirmed redshift of 13.2 and a corresponding age of the universe of just 320 million years at the time. Other ultra-distant galaxies have been found by James Webb, with multiple other JADES galaxies found younger than 500 million years, and significant competitors in the same class of distances. The galaxy JADES GSZ13-0 is the name of the current record holder, but it's fully expected that with more data, deeper data, and greater sky coverage, this record will soon be broken, and likely many times over before all is said and done. One of the largest, deepest views that James Webb has taken of the universe, at least so far, comes from the SEERS collaboration, the Cosmic Evolution Early Release Science Survey. By surveying a very large area of sky of 100 square arcminutes, SEERS aimed to photometrically observe extraordinary numbers of galaxies within that field. The rationale is that this photometric survey would identify a number of galaxy candidates that might be among the earliest and most unusual galaxies in the universe, and then the best candidates would be able to be followed up with Webb's spectroscopic capabilities. Against all expectation, the premier space observatory has found something very strange. It didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. As Michaela Bagley of the University of Texas, one of the leading CER's researchers, said, "The theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early." Such the high number of early galaxies detected suggests that there's something we don't yet understand about galaxy formation, and how that process has changed between billions of years ago and now. The fact that the galaxies are brighter than expected is intriguing too, and could have several explanations. These galaxies could actually be giving off more light, or they could be more massive, or it could be a combination, as the two factors are related. The early universe had galaxies with potentially as many stars as the Milky Way, and we don't have an explanation for how these stars could have formed so early or in such great numbers. There's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. On the other hand, note that the most distant galaxies that we've ever discovered are just the tip of the cosmic iceberg, the brightest and most massive galaxies found at these extreme reaches of the universe. As James Webb continues to collect more and more data, the distant universe will continue to come into focus, answering some of our present questions and opening up new avenues to investigate. A full understanding of our universe, from the earliest times imaginable all the way to the present day, is finally closer than ever to being within reach. Interestingly, beside the most distant galaxies, most recently, James Webb stuns the whole world with new high-definition look at exploded star. Look at this! Supernova remnant Cassiopeia A, or Cas A, gleams in a new image from James Webb like a shiny round ornament ready to be placed in the perfect spot on a holiday tree. For those who don't know, the Cas A supernova remnant is located 11,000 light-years away in the constellation Cassiopeia. It's estimated to have exploded about 340 years ago from our point of view. While all is bright, this scene is no proverbial silent night. Webb's near-infrared camera, or NIR cam view of Cas A, displays this stellar explosion at a resolution previously unreachable at these wavelengths. This high-resolution look unveils intricate details of the expanding shell of material slamming into the gas shed by the star before it exploded. Cas A is one of the most well-studied supernova remnants in all of the cosmos. Over the years, ground-based and space-based observatories, including NASA's Chandra X-ray Observatory, Hubble Space Telescope, and retired Spitzer Space Telescope, have assembled a multi-wavelength picture of the object's remnant. Astronomers have now entered a new era in the study of Cas A. In April 2023, Webb's Mid-Infrared Instrument, or MIRI, started this chapter, revealing new and unexpected features within the inner shell of the supernova remnant. Many of those features are invisible in the new NIR cam image, and astronomers are investigating why. Infrared light is invisible to our eyes, so image processors and scientists translate these wavelengths of light to visible colors. In this newest image of Cas A, colors were assigned to different filters from NIR cam, and each of those colors hints at different activity occurring within the object. At first glance, Webb's NIR cam image may appear less colorful than the MIRI image. However, this simply comes down to the wavelengths in which the material from the object is emitting its light. The most noticeable colors in Webb's newest image are clumps represented in bright orange and light pink that make up the inner shell of the supernova remnant. Webb's razor-sharp view can detect the tiniest knots of gas, comprised of sulfur, oxygen, argon, and neon from the star itself. Embedded in this gas is a mixture of dust and molecules, which will eventually become components of new stars and planetary systems. Some filaments of debris are too tiny to be resolved by even Webb, meaning they are comparable to or less than 10 billion miles across. In comparison, the entirety of Cas A spans 10 light-years across, or 60 trillion miles. According to Danny Milisavljevic of Purdue University, who leads the research team, with near-infrared camera's resolution, we can now see how the dying star absolutely shattered when it exploded, leaving filaments akin to tiny shards of glass behind. It's really unbelievable, after all these years studying Cas A, to now resolve those details, which are providing us with transformational insight into how this star exploded. When comparing Webb's new near-infrared view of Cas A with the mid-infrared view, its inner cavity and outermost shell are curiously devoid of color. The outskirts of the main inner shell, which appeared as a deep orange and red in the MIRI image, now looked like smoke from a campfire. This marks where the supernova blast wave is ramming into surrounding circumstellar material. The dust in the circumstellar material is too cool to be detected directly at near-infrared wavelengths, but lights up in the mid-infrared. Researchers say the white color is light from synchrotron radiation, which is emitted across the electromagnetic spectrum, including the near-infrared. It's generated by charged particles traveling at extremely high speeds, spiraling around magnetic field lines. Synchrotron radiation is also visible in the bubble-like shells in the lower half of the inner cavity. Also not seen in the near-infrared view is the loop of green light in the central cavity of Cas A that glowed in mid-infrared, nicknamed the Green Monster by the research team. This feature was described as challenging to understand by researchers at the time of their first look. While the green of the Green Monster is not visible in NIR-CAM, what's left over in the near-infrared in that region can provide insight into the mysterious feature. The circular holes visible in the MIRI image are faintly outlined in white and purple emission in the NIR-CAM image. This represents ionized gas. Researchers believe this is due to the supernova debris pushing through and sculpting gas left behind by the star before it exploded. Researchers were also absolutely stunned by one fascinating feature at the bottom right corner of NIR-CAM's field of view. They're calling that large striated blob baby Cas A because it appears like an offspring of the main supernova. This is a light echo, where light from the star's long-ago explosion has reached and is warming distant dust, which is glowing as it cools down. The intricacy of the dust pattern and baby Cas A's apparent proximity to Cas AA itself are particularly intriguing to researchers. In actuality, baby Cas A is located about 170 light-years behind the supernova remnant. There are also several other, smaller light echoes scattered throughout Webb's new portrait. Notably, this isn't the first time James Webb has turned its sharp eyes on a supernova. Just a few months ago, the Time Machine has gazed at the Crab Nebula, a supernova remnant located 6,500 light-years away in the constellation Taurus. Since the recording of this energetic event in 1054 CE by 11th century astronomers, the Crab Nebula has continued to draw attention and additional study as scientists seek to understand the conditions, behavior, and after effects of supernova through thorough study of the crab, a relatively nearby example. Using Webb's NIR-CAM and MIRI, a team led by T. Temim at Princeton University is searching for answers about the Crab Nebula's origins. At first glance, the general shape of the supernova remnant is similar to the optical wavelength image released in 2005 from NASA's Hubble Space Telescope. In Webb's infrared observation, a crisp, cage-like structure of fluffy gaseous filaments are shown in red-orange. However, in the central regions, emission from dust grains, yellow, white, and green, is mapped out by Webb for the first time. Additional aspects of the inner workings of the Crab Nebula become more prominent and are seen in greater detail in the infrared light captured by Webb. In particular, Webb highlights what is known as synchrotron radiation, emission produced from charged particles, like electrons, moving around magnetic field lines at relativistic speeds. The radiation appears here as milky, smoke-like material throughout the majority of the Crab Nebula's interior. This feature is a product of the nebula's pulsar, a rapidly rotating neutron star. The pulsar's strong magnetic field accelerates particles to extremely high speeds and causes them to emit radiation as they wind around magnetic field lines. Though emitted across the electromagnetic spectrum, the synchrotron radiation is seen in unprecedented detail with Webb's NIR-CAM instrument. To locate the Crab Nebula's pulsar heart, trace the wisps that follow a circular ripple-like pattern in the middle to the bright white dot in the center. Farther out from the core, follow the thin white ribbons of the radiation. The curvy wisps are closely grouped together, outlining the structure of the pulsar's magnetic field, which sculpts and shapes the nebula. At center, left, and right, the white material curves sharply inward from the filamentary dust cage's edges and goes toward the neutron star's location, as if the waist of the nebula is pinched. This abrupt slimming may be caused by the confinement of the supernova wind's expansion by a belt of dense gas. The wind produced by the pulsar heart continues to push the shell of gas and dust outward at a rapid pace. Among the remnant's interior, yellow, white, and green mottled filaments form large-scale loop-like structures, which represent areas where dust grains reside. The search for answers about the Crab Nebula's past continues as astronomers further analyze the Webb data and consult previous observations of the remnant taken by other telescopes. Scientists will have newer Hubble data to review within the next year or so from the telescope's re-imaging of the supernova remnant. This will mark Hubble's first look at emission lines from the Crab Nebula in over 20 years and will enable astronomers to more accurately compare Webb and Hubble's findings. But even with all this information, there's still a problem that emerges when it comes to the Crab Nebula, the problem of mass. Astronomers are a big fan of the idea that a star's initial mass, the amount of mass that it has when it's born, is what determines its eventual fate. We know that this is largely true, as stars like the Sun, which generally includes stars between 40% and 800% the mass of the Sun, will burn through their core hydrogen, evolve into red giants, begin fusing helium in their cores, and then will gently die, blowing off their outer layers into a planetary nebula while their cores contract to form a white dwarf. The lowest mass stars, which include stars below 40% of the Sun's mass, will have time to fully convect, bringing burned material out of the core and into the star's outer layers, while bringing new hydrogen-rich material into the core. When these stars run out of hydrogen, they won't get hot enough to fuse helium, leading to a state of slow contraction, ending in a white dwarf. But the highest mass stars, born with 8 solar masses of material or more, will not only ignite hydrogen and then helium burning in their cores, but will go on to fuse carbon, neon, oxygen, and then silicon and sulfur, eventually dying in core collapse supernovae, leading to a neutron star for the lower mass varieties and a black hole for the more massive ones. That's where the big puzzle arises. There just isn't enough mass in the Crab Nebula, as inferred by these multi-wavelength observations, to explain its core collapse supernova and neutron star fate. The Crab pulsar, or the neutron star at its core, comes in at only 1.4 solar masses. From all the previous multi-wavelength data, we've been able to constrain the mass of the Crab Nebula, the nebulous material that doesn't include the central pulsar, to be between 2 and 5 solar masses, with obviously a fair amount of uncertainty there. But observations at greater distances around the nebula, where it's plausible that a shell of material could have been blown off in earlier stages, reveal a complete absence of any detectable material at all. There's no shell, plasma, or diffuse gas present to the absolute limits that our instruments can see. Even if we take the high mass value for the Crab Nebula, that still doesn't give us enough matter or material to trigger a core collapse supernova. There's got to be a flaw in our understanding somewhere, but exactly where is a big mystery. Could we be modeling the nebula wrong? If so, improved data can help us better estimate the total mass of the Crab Nebula. Could we be measuring the mass of the neutron star incorrectly? It's possible, but not by that much. The most massive neutron star ever found is only slightly heavier than 2 solar masses. Could there be material that was ejected long ago that's now been blown away? Perhaps. But that doesn't align very well with our understanding of stellar evolution in the late stages of a massive star's life. Could we be misunderstanding the conditions for a supernova? It's unlikely, but we've observed so few in detail that we have to consider it. Fortunately, we're about to get an assist from the full James Webb view, now finally available, of the Crab Nebula. The greatest new detail that's finally revealed with Webb imaging, something that quite notably James Webb's predecessor, Spitzer, could not reveal, is the first complete and comprehensive map of the dust distribution within the Crab Nebula. Since the spectral features that reveal individual elements only apply to individual atoms, not to dust grains that may contain those elements, it's possible that we've failed to sufficiently account for dust in previous observations. As you can see, above the central yellow, white, and green filaments that appear in Webb's infrared image are dust-dominated and could be incredibly rich in material. Also, in Webb images, as opposed to the optical Hubble images, you can see what appears as grayish-white smoke filling in the interior of the cavity carved by the expanding gases. This isn't smoke by any means, but rather a phenomenon known as synchrotron radiation, where fast-moving electrons are accelerated by a strong magnetic field, and the action of that magnetic field causes the electrons to radiate electromagnetic radiation as they pass through the magnetic field. It just so happens that the wavelength range that the synchrotron radiation comes in matches the wavelengths that James Webb is sensitive to. On the outskirts of the nebula, you can see that the smoke-like wisps are curved and pinched, like they're being funneled into a central disc-like shape. While there are numerous possible explanations for this appearance, one tantalizing one is that there's a belt of dense gas confining where the supernova's winds can flow. This is another possible store of massive material that has gone undetected thus far. There are also hotter, heavier elements revealed by Webb observations, particularly on the outskirts of the nebula. The red-orange filaments of gas seen by James Webb trace out doubly ionized sulfur atoms, which peter out at smaller distances than the lighter hydrogen atoms that Hubble was sensitive to, farther toward the nebula's outer edges. But perhaps, most interestingly, there are novel details revealed about the very heart of the nebula, in the region where the pulsar is located. The smoke-like wisps located toward the center trace out the magnetic field lines created by the central pulsar, and you can see many curved wisp-like features all grouped together, indicating the locations where the magnetic field is strongest. This represents material still being transported away from the central regions of the nebula, farther toward the outskirts. You can also see by looking at the full field view of these images that there's an asymmetry. The filaments appear to be lengthened toward the upper right of the pulsar, while simultaneously being relatively shortened in the opposite direction. Although it's still worth additional efforts investigating this phenomenon, it's notable that the pulsar itself is moving toward the top right of the nebula. Perhaps the extent of the nebula has something to do with the motion of the central stellar remnant. Hubble hasn't taken another look at the Crab Nebula since the early 2000s, more than 20 years ago. But that's about to change. Just as James Webb is observing the nebula now, it's important to get simultaneous data from Hubble in order to paint a more complete picture of this fascinating region of the sky. Perhaps, with new, superior data from both observatories combined, we'll not only be able to map out the various details within it, but come up with a more satisfactory accounting of where all the mass is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.